Welcome to Calculus and Differential Equations with Taylor series. So again, the idea here is since we know how to, or since we can differentiate and integrate Taylor series term by term, we can work with the Taylor series if we're instead of the original function, if we don't know how to integrate as the function is written. So we can work with Taylor series when we are unsure how to integrate a function. So one of the more famous versions of a function that is very challenging to integrate is the integral of e to the x squared dx. So recall, or you may have seen, that the integral from e to the x squared dx cannot be integrated using any of our usual techniques. So cannot be integrated using any of our usual integration techniques. However, we do know how to express e to the x squared as a series, right? But we saw in the previous video that e to the x squared is equal to the sum from n equals 0 to infinity of x to the 2n over n factorial. So that means that the integral of e to the x squared dx is the same as the integral of the sum from n equals 0 to infinity of x to the 2n over n factorial. This, and then dx. This we can integrate term by term. So if we integrate term by term, then we wind up getting that this is equal to some constant c plus the sum from n equals 0 to infinity of x to the 2n will go up to x to the 2n plus 1. Then we would, of course, have to divide by that new power. And our n factorial comes along for the ride. So even if we cannot directly integrate a function, if we know how to write it as a series, then we can integrate it in series form instead. There is, in fact, no way to write a simple function for the integral of e to the x squared dx. This is as simple as it gets. So now let's veer back to differential equations. So recall that we saw a population model back in section 8.6, with p prime equal to 0.004 times p, and p of 0 equal to 400,000, which had solution p of t equal to the sum from n equals 0 to infinity of the nth derivative of p evaluated at 0 over n factorial times t to the n. Our job is to find a function to match this series. So we had seen, we saw when we worked with this model before, we saw that the nth derivative of p evaluated at t was just equal to 0.004 times the previous derivative evaluated at t. We wound up just getting that this is equal to 0.004 raised to the nth times p of t. So we had the nth derivative evaluated at 0 as just 0.004 raised to the n times p of 0, or 400,000 times 0.004 raised to the n. And we had gotten that p of t was equal to the sum from n equals 0 to infinity, therefore, of 400,000 times 0.004 raised to the n, all over n factorial times t to the n. And we had rewritten this as 400,000 times the sum from n equals 0 to infinity of 0.004 raised to the n over n factorial times t to the n. Okay. But note that 0.004 raised to the n over n factorial times t to the n is precisely the same as 0.004 t raised to the n all over n factorial. So we have that p of t is therefore simply 400,000 times the sum from n equals 0 to infinity of 0.004 t raised to the n over n factorial. But this series, that sum from n equals 0 to infinity of 0.004 t raised to the n over n factorial, this is just the series for e to the x, where x is 0.004 t, or e to the u, let's say, with u equals 0.004 t. And so what we get is that p of t is simply 400,000 times e to the 0.004 t. So ultimately in differential equations, you'll get shortcuts for this where you can just jump straight to that answer, more or less. you won't have to pass through the series. But we will have other differential equations where you will need to work with a series to solve. But now that we do recognize some common series, we can kind of solve our series, and then if we recognize a common series, revert back to a more explicitly written function. So that is Taylor series and its various uses.